We've talked a little bit about lines in space, but now we want to talk about planes in space, which are kind of easy to visualize, but maybe a little more complicated to think about analytically. So I want you to recall something important, which is that if U is orthogonal to V, then their dot product will be equal to 0. And that'll become important. You'll see why that's important later. So when we talk about a plane in 3D space, what we're really saying is that this is an object that can be described by two vectors. Usually when we think about locations or objects in space, we might need three vectors because we're dealing in 3 dimensions. But a plane has the specific property that you only need two vectors to describe it. So in this case, if I have this vector 1 and this vector 2, I can describe every plane in the space by those two vectors. So we think about, and no, I want to point out that those vectors may not be your I, J, K vectors. If you think about the vectors I and J, no K, that's the XY plane. You can think about that as, those being describing just the XY plane. Or if you think about just the JK, that's the YZ plane. So you can always think if you have two vectors, you can describe a plane, but you can't describe every piece in the space. But anyway, so planes have a very specific property. And that's if I have some point, or if I have any 2 points in the plane, I can always draw a vector that still lies in that plane. And there's this extra piece of information, this normal vector. So a normal vector is a vector that has this interesting property. It's orthogonal to every vector in the plane. So if I take any 2 points in the plane, the normal vector is orthogonal to all those directed line segments. And if you think about that, that kind of makes sense. If I take this first vector and I take that second vector and I think about the plane that it would make, but instead I took them and I took their cross product. So I took those two vectors and I generated a third vector with the cross product. That vector would be orthogonal to both of those generating vectors. And if I just slid that vector or that normal vector across the plane, it stays orthogonal to every point in the plane, right? If the plane was sloping down and I had some sort of normal vector, it wouldn't matter how I slid it, it would still stay orthogonal. So there's a very specific property there that since we know that this particular vector is orthogonal to every piece in the plane, we can use that to construct equations for how to describe planes. Well, so if we move over here, what we see is that if I know a point in the plane, some sort of x0, y, it doesn't matter, it's any point in the plane, and I know what the normal vector looks like, well then I can write this thing in a standard form. I just fill out this piece here. I say a times x minus x0, b times y minus z0, and c times z minus z0 equals 0. And you may think to yourself, well, why does that have to be equal to 0? Why is that the standard equation of the plane? Well, it comes from the nature of the dot product. If I think about this as, these are the components, and I were to dot it with some vector, x minus x0, and these were the components of that other vector. So I'm going to draw on here again. If I said something like v is if I said that vector was described this way, which kind of makes sense because any x, y, z that plugs in here is also a point in the plane. So this right here is just the directed line segment from any point in the plane to that point. So since we know that the dot product, so this would be n dot v, so we know the dot product has to be 0. This just comes as a natural consequence. We didn't conjure it out of the air. We just thought about it and constructed something that fit that narrative. So now the nice thing is equations don't have to be in standard form for us to easily see the normal. This is going to come up in like homework problems or just in general, where you may see an equation that looks like this and you say, well, I don't have, it doesn't look like that. So what's the normal vector? Well, the normal vector is just the coefficients on those variables. It could look like this, it could look like that, it could look like that, but all of them have that same normal. And if you really, really thought about it, you could figure out an algebraic way to make specifically something like, you can make it look like that. You'd have to maybe shift it, and you may have to adjust what your starting point is a little bit to figure out the best way to do it. But it all really describes the same plane. Or it describes a plane that you'd have to figure out the best way to fill that out. But either way, the moral of the story is, if you see something in standard form or you see it in these sort of alternate forms, we can always determine the normal vector.